Okay. So, I mean, you have a set of steps there that you can follow, but they're not overly meaningful until you really think about what's actually happening, right? At least behind the scenes. So we talk about the explicit form of a derivative, and we talk of a function, and we talk about the implicit form. And really, it's just a simple idea. An explicit form is where you have one variable solved in terms of another. I mean, you can think of it that way. But it's also like that old thought where you would never define a word by using the word in the definition, the word itself. All right? So the idea of an explicit form is the definition of y is stated in other terms, not involving y. All right? So if I have an equation that's solved for one variable strictly in terms of the other variable, or other variables, if we're working with multivariable situations, then you're looking at an explicit form of a function or an equation. But if it's not, if there's any kind of ambiguity there, then we call that the implicit form. All right. Now, in many situations, you could just move some things around when you're given an implicit form to come up with the explicit form, and then you just go back to the techniques that we were using previously. But then you come across some situations where, if you look at the first example, yeah, you could solve that for y in terms of x. It's not going to be pretty. And then you got to do the calculus after that. Still not going to be pretty. You probably don't want to go down that road. All right? So maybe the implicit form can be differentiated using a technique. And we know that it can be because you see the steps right there. Right? It's just a matter of carrying them out. If you go to example 2, you can see another type of function. Well, it's still an implicit form, but it's not like number 1 where you can look at it and say, well, I could solve, if worst case scenario, I'll solve for y in terms of x. I mean, for this one, it's like, good luck with that. Right? There is a way to do it. It's just, I mean, if the last one wasn't going to be pretty, this one really isn't. You'd actually, because it's kind of like an extension topic in Algebra 2. And maybe if you're in honors, you would touch on something like this. But you would actually have to look at this equation as a quadratic where the variable is y, and you would treat any x as a coefficient of y. And then you'd use completing the square quadratic formula to solve for y in terms of x. So if the last one wasn't pretty, this one really wouldn't be. Right? So you'd actually have to look at it. I'm not going to do it, but I'll show you what the structure would be like. You'd have to look at it like x y squared plus x squared y and then you'd have the plus 2 off at the end equals 0. And we would treat this as the a value, the b value, and the c value in the quadratic formula, or completing the square. I mean, it's a fun algebraic exercise, but it's not the preferred way to go about it, especially if you can find the derivative in its original form without any adjustment. All right? So that's sort of the motivation behind why we're doing this. We're looking to do it in such a way that we don't have to mess around with it too much algebraically initially. All right? So going back to that explicit form, if I needed to take the derivative of this, it'd be very straightforward. After a very minor adjustment, I'd write this as y equals x to the negative first power. And then the derivative of that would just be, you could use y prime or dy dx. I'll use dy dx. Would be equal to negative 1x to the negative second, which you can then clean up a little bit if you want. Right? You know, make it into a fraction, negative 1 over x squared. Right? Now, we didn't realize this at the time, but every time we take the derivative of a function, we were applying the chain rule. It's just it wasn't always necessary, right? Because x in this case is a linear function, right? So just the x itself. You think about what we would do if we were to apply the chain rule to something like this. You'd have your blob, big old blob. Blob to the negative first power would be -1 blob to the negative second power. But then we'd have to multiply by the derivative of blob. All right? So we would multiply by the derivative of whatever is in the blob with respect to x. I don't want to do this. No. Okay, fine. I'll answer it. Oh, boy. Standing up. Gotta get over here. Oh, boy. Oh, almost tripped there. Every time. So, the derivative of that blob, the blob was just the x. The derivative of x was equal to 1. So it didn't factor into the solution in any way. So it was irrelevant to the point where we wouldn't even talk about it. Which is why this is the first time you're hearing stuff like that. It was irrelevant. It didn't matter. Right? So then the question becomes, well, why does it matter now? Well, now we're moving on to more advanced topics. We consider instances where x may not just be the linear function y equals x. X could be another function, a function of a different variable. Maybe x is in terms of t. You know, because we have a definition here. Y is the reciprocal of x. That's what y equals 1 over x means. All right, you take x, flip it over, you get y. All right, so if x is 2, y is 1/2. All right, but what if x is equal to the cosine of t? Now you have a function that requires a derivative. All right, but even more basic than that, what if we're working in a different coordinate system? All right, so in the ordinary Cartesian plane xy, every unit is equivalent to one value, all right, which makes sense. All right, but you've scaled graphs before. All right, what if every unit is not equal to just one value, the number 1? What if every unit is equal to the cosine of whatever the x values were? All right, you could change an entire coordinate system that way. It's very difficult to visualize that sort of thing, but we call it, well, not everybody does, but it's a linearization method. All right, so what you do is, like, for example, if you have a logarithm and create a log scale on a graph. So instead of counting by ones, you count by the log of 1, log of 2, like whatever. Just something in terms of logs, all right? Or powers of 10 for an exponential. That linearizes the function. So instead of having a curved look, it would have a linear look. It's still a logarithm. In an ordinary Cartesian xy plane, it would still be a curve, a curved logarithmic function. But if you transport to the logarithmic universe, what was a curve is now a line, right? Because in the rules of that universe, the basis of that structure is logarithmic. So every unit is measured in different values rather than 1, 2, 3. It's log of 1, 2, 3. Right? So the appearance changes. It's warped reality, basically, but that's how it would work. So in that context, would the derivative of x with respect to x be equal to 1? I don't know. Right? Depends on what the scale is. Right? Because if the scale is variable, if it's based on some variable quantity, then I would have a meaningful derivative, like the chain rule gives us. All right? So that's why we would say the blob thing. You know, like, what is the blob? The blob is the coordinate change. It's a change in variables, it's a change in structure of the universe. All right? So when I say instead of 1 over x, I'm saying 1 over cosine of x. I'm saying let's move into a universe where instead of the x-axis being measured in terms of 1, 2, 3, it's measured in terms of cosine 1, cosine 2, cosine 3. Right? It's changing the structure of reality. Right? So in this case, it didn't matter at all because you'd say dx is equal to 1 and cancels away, but it might have more meaning depending on what the variable is or represents. All right? So how do we handle those situations? We handle it implicitly. All right? But if you look at the implicit form, xy equals 1, it's really the same function. Or, well, same equation. Right? You'd have to evaluate it to see if it's a function. All right? But we can find the derivative of this without solving for y in terms of x. Right? Just making the assumption that x and y could be something other than what we expect them to be in this universe, right? Where x is equal to just the line y equals x, right? Maybe x is equal to the curve y equals the cosine of x. We don't know, right? Cosine of t, cosine of pick a variable, it doesn't matter, right? So we treat it as if it's a hidden function, right? So it's a hidden chain rule situation. So what we would do is apply the product rule, because we're looking at two functions being multiplied here. First times the derivative of the second plus the second times the derivative of the first. All right. So x times the derivative of y with respect to x. Because again, I don't know what y is. So all I can say is the derivative of whatever y is with respect to x. Plus my second function times the derivative of the first, one thing that holds over nicely regardless of what universe you're living in is the relationship involving constants. Constants always have a derivative of 0. Right? It's unchanged value, right? It's a fixed quantity. If we move into the cosine universe, maybe 1 becomes cosine of 1. It's still constant, right? So the derivative there goes down to 0. So then what we would do is solve this for dy dx, because ultimately that's what they're asking for. I use the bracket notation, but this could easily be written as x times dy dx plus y times dx dx is equal to 0. So then you look at it and evaluate it based off of the universe that you're in, right? That goes to domain and range. Do you know what the x values really are, what the y values really are? We don't know why, but we do know that we can express it as a definition dependent on the value of x, right? So it's like, maybe it's a complicated equation like the one on the next page where you say, I can't personally solve for y in terms of x, but I know somebody can. So there's a solution out there. So I don't know what y is, but if I know x, then I can come up with the definition of y based off of that. All right. So the independent variable x is really the steering wheel of this whole thing. All right. So you can look at it that way and say, all right, well, ultimately I'm trying to solve for dy dx. Get dy dx alone. You could also look at it and say, well, dx dx, I mean, forget about all this universe stuff. Isn't that a quantity divided by itself? Anything divided by itself is going to be equal to 1. If I change the universe, it would be a different story. If someone comes along and says x really is the cosine of t, then I'd have a problem. I'd have to do something about that. But that information is not given to us, right? So you can cancel it. So you can cross out the dx dx, but cautiously, right? So you got to be considering, okay, what is x? Is it just the line y equals x in the ordinary Cartesian xy plane? Yes, cross it out. I'm not sure, leave it in. No, leave it in. All right? So really it's, am I positive that it's just x? X, sometimes a cigar is just a cigar. If that's the case, then cross it out. If you're not sure, leave it in. or otherwise leave it in. All right? So only if you're positive that it's just the line y equals x. All right? So solve for dy dx. Well, I would be subtracting this, so that's going to the other side. So x times dy dx would be equal to negative y times dx dx. I guess I could go the other way. Really doesn't matter. I started doing it this way. I mean, it's a proportional relationship. It doesn't matter which one you move to which side. All right, so dx dx. And then divide both sides by x. All right, so we'll multiply both sides by 1 over x. So dy dx would be equal to negative y over x times dx dx. Or we could just say negative y over x. All right, I made the problem, so I can tell you that the x is what it appears to be. Just a linear equation, y equals x. So dx dx would cancel away. But again, if you're not sure, you leave it in. All right, so my derivative here would be negative y over x, and you're like, well, that's not what we got for the first one, or the other iteration of this. That was negative x to the negative second times dx dx. Well, what's the difference? Well, here I'm defining the derivative in terms of both x and y. So if I know the value of y, or the value of x, and or the value of x, then I can make a substitution. If I solve my original equation for y in terms of x, then I can make a substitution, right? But that defeats the purpose. If I solve the original equation for y in terms of x, then it's like, well, why not just find the derivative this way? You know, like, why do any of this stuff? All right, so you have a lot of wiggle room here, but the implicit form very often is going to look vastly different in terms of the derivative than the explicit form. All right, but this is a simple case. This one is really like, okay, easy, not too bad. Just follow the steps. All right. Now, I understand that the theory, my explanation of the theory involved a lot of hand waving, a lot of imagine this, you're transported to a different universe. The best you can come up with is like, all right, whatever recent Marvel movie addressed that, you know, like, is that what he's talking about? Yeah, actually it is. But maybe it doesn't make sense. If it doesn't make sense, it will eventually. It just takes a little time. I can tell you that this is one of the few topics in calculus that I didn't understand the first time through. All right, the theory. So I followed the steps until it made sense. All right. In fact, I had to go to extra help for this one. All right. So the only time I ever stayed after school when I was in high school was when I got detention, which was unfortunately fairly often. But I did choose to stay after one time in my high school career, and that was for this topic. All right. And the teacher just explained it really the same way in extra help. Didn't help, but I listened. I tried. And then one day I'm sitting there doing problems, just thinking, and it just clicked. All right? This is one of those topics. It's weird, but it is what it is. So the recipe for success, to get things right, anytime you take a derivative, slap on a d whatever dx. All right. So if variable's x, dx dx. If the variable's y, dy dx. All right. So looking at example 1, I mean, you can follow the steps too, but you know, that's more based off the theory. So if I find the derivative of this, I have x squared plus y squared is equal to 16. I'm going to look at this as if it's just an ordinary run-of-the-mill derivative problem, something that we've been working on for a while. All right. I see power relations. All right. X squared and y squared. I'm going to take the derivative of each of those using the power rule. All right. So the derivative of x squared would be 2x. Or at least last week it would have been. But because I took a derivative and the variable's x, I'm going to slap on a dx dx. And I'm just going to do the same thing with the y. The derivative of y squared last week would have just been 2y. Now it's going to be 2y, and then slap on a d whatever dx. The whatever here is the y. All right, so dy dx. It's addition, so add them together. Derivative of a constant is equal to 0. And that's all there is to it. Right? I mean, you're going to solve for dy dx, but you've successfully taken the derivative now. The rest is just algebra. All right, so if this is ordinary coordinate plane, Cartesian plane, which it is, I mean, we recognize this as x squared plus y squared is 16. That's a circle with the center at the origin and a radius of 4. All right, in terms of the scale, how would I graph it? Well, I'd go out in terms of x, 1, 2, 3, 4, whatever. Left and right, go up and down. So it's just we're in the ordinary universe here. So I can wipe out the dx dx. We'll be looking at 2x plus 2y dy dx is equal to 0. I'm just going to solve for the dy dx now. So I'm going to subtract the 2x from both sides. And then multiply both sides by 1 over 2y, or just divide both sides by 2y. It's the same thing. All right, so we'd be looking at, when you simplify it, dy dx is equal to negative x over y. So that's my derivative. All right, very, very quickly, you don't have to write this down. I'm just going to show you off on the side what you would have had to do if you were to tackle this problem without using implicit differentiation. All right, so the first thing you'd have to do is solve for y in terms of x. So plus or minus the square root of 16 minus x squared, which would be the same thing as plus or minus 16 minus x squared to the 1/2 power. You'd have to use the chain rule. So dy dx would be plus or minus 1/2 16 minus x squared to the negative 1/2 times the derivative of whatever is contained on the inside, which would be negative 2x, which you could then simplify if you want, but I mean, the point is proven. All right, one, you had to do the work to get it into explicit form to begin with. All right, if you see it right away, that's great. If not, then it might take a minute. And then you had to use the chain rule to differentiate, and you got something that's vastly more complicated than what we came up with using implicit differentiation. Right? So in either situation, if I know particular values, I can come up with the slope. Because again, dy dx, whether it's implicit or explicit, it's still a measure of slope. So if I know x and y, so if I know a coordinate on this graph, then I just pop it in. It's the ratio of x to y negated, and that's my slope. Here, a little bit more work, right? And depending on your strengths and weaknesses with algebra, it might be the kind of approach that is destined for failure, like an algebraic mistake along the way.
For like solving it in the explicit way, like how you did there, would we still need to simplify after you get that like long derivative answer?
This one?
Yeah.
You wouldn't, because it would just be substitution at that point.
Oh.
Yeah. So now that is a circle. X squared plus y squared is equal to 16 with a radius of 4. So I'd plot the center, go up and down, left and right 4 units. Conic sections are usually easier to graph without a calculator, just because of the structure of circles, ellipses, and things like that. Right? Hyperbolas, parabolas. When you have to solve for y in terms of x just to put it in a calculator, things get a little dicey. All right. So draw a circle. Let it autocorrect so it looks nice. So any point on the circumference of this circle is going to have, it's going to be a point of tangency. In fact, the first time you learned about tangents was in geometry, and it was usually, typically, how a line relates to a circle. All right, so this would be a tangent line, for example. So if I know any of the points on this circle, then I would know the tangent, the slope of the tangent line. Good thing about circles that are centered at the origin is even the crazy decimal values along the circumference are pretty easy to figure out, at least for certain angles, because it's all unit circle. Right? So if you know in the unit circle at 45 degrees that the coordinate on the circle is radical 2 over 2, comma radical 2 over 2, for a radius of 4, you just multiply that coordinate, you dilate it by a factor of 4. So it'd be 2 radical 2, comma 2 radical 2. So I could figure out lots of information based off of the fact that it's a circle and that very simple derivative equation that we came up with. Right? Now in this one, they're just asking for instances where the graph has a horizontal and vertical tangent. So horizontal tangent would be a turning point on the high side or the low side. So this would be a horizontal tangent, and we'd have another one down low. All right, it touches a circle in exactly one location, crappy drawing aside. And it's also horizontal. All right, you'd also have your vertical tangents. Here and here. All right, they're asking for the instances in which, in the circumference of a circle where that happens. Visually, we can make the determination. We have 0, 4, 0, negative 4. So we don't really need calculus for this, but I'll show you how we would use calculus. 4, 0, negative 4, 0. All right, so that works. Instances in which it's, the curve has horizontal vertical tangents, so it's accounted for. We got the answer. All right, but if you had to work off the derivative, well, we know horizontal lines have a slope equal to 0. All right, so we would want to know the instances in which dy dx is equal to 0. I would rather work with this equation, we call it a differential equation, than this one. So I would say negative x over y is equal to 0, and then solve for x. You can solve for either variable. It just naturally works out that x is the choice here. All right, because when you cross multiply, the y cancels away. You're left with negative x equals 0, which means that x is equal to 0. So any instance on the graph where x is equal to 0 would have a horizontal tangent. You could get that visually, or we go back to the original function equation, replace the x with 0, and solve for y. You get y squared is equal to 16, which means y is equal to plus or minus 4. All right, so we have the coordinate pair. X positive 4, x negative 4, with the x being 0. So therefore, we would say 0 plus or minus 4. In the case of vertical tangent, vertical lines have slopes that are undefined. So I would set dy dx equal to, well, you could choose any constant you want, but it'll always simplify down to 1, regardless of what constant you choose. I mean, if you decide to make it equal to 376 over 0, it'll still work out to simplify down to 1 over 0. All right, so why not just start with the 1 over 0? So negative x over y, cross multiply, you get y is equal to 0. Same deal, make a substitution, replace the y with 0, solve for x, x squared plus 0 squared is equal to 16, making x squared equal to 16, making x equal to plus or minus 4. So my coordinate pair, plus or minus 4 comma 0. All right. Definitely a lot easier than it would be if you had to solve using the explicit form. All right. Still doable. You could still do this work for some equations and come up with a derivative that's equivalent. It'll do all the same stuff. The problem is you get to something like number 2 and it all falls apart. All right? Because if you don't have the skills necessary to isolate y, solve for y in terms of x, then this one's all over. All right? So it's a technique that you got to know. All right? So in the short term, we're saying anytime you take the derivative, you just slap on a d variable dx, whatever the variable is, all right, through multiplication. And that's really all there is to it. Little notation issue for number 2, that shouldn't say f prime of 2. It's not a function, not necessarily a function of x. So that shouldn't be there. Wipe it out. All right, so for this one, you see we have products, x squared y squared x, and then we have the constant. We're going to use the product rule. We'll do one at a time. So x squared times y, first times the derivative of the second, plus the second times the derivative of the first. So the first, in its original form, times the derivative of the second. Well, the derivative of y normally would be 1. So we would say 1, but then slap on a dy dx if you're going the procedural route. Alternatively, you could say, well, I'm taking the derivative of y with respect to x. That's the same as saying dy dx. All right, plus the second function, y, times the derivative of the first, which would be 2x, slap on a dx dx. All right, then we move on to the second set of factors and do the first times the derivative of the second plus the second times the derivative of the first all over again. All right, so this is a fairly lengthy one, but we still follow the process and still get it done. So we have the plus built into the equation. First is y squared times the derivative of the second. I could say dx dx just because I'm taking the derivative of x with respect to x, or I could say, well, last week the derivative of x is 1, but now I got to slap on a dx dx. All right, so times 1 times dx dx plus my second function x times the derivative of the first, so 2y, slap on a dy dx. The derivative of negative 2 is constant, so the derivative of a constant would be equal to 0. All right. So that's the calculus part of it. As you go forward, you start realizing that the calculus only happens in generally one step in any problem that you do. Almost everything else is algebra, right? Unless you're using a technological approach. But here, our only job is to try to isolate the dy dx. Now there's 2 of them, so I got to consolidate them also. All right. But before I do that, they didn't tell us to simplify, but it's in our best interest to do that. So x squared dy dx plus 2xy. The dx dx, they didn't give us any information regarding the nature of x, so there's no reason to think that we're in some sort of alternate universe. So dx dx just goes to 1. We make that assumption. All right. Plus y squared, which, by the way, means that there will be instances where I say x is something else, and we'll have to account for that. All right? So y squared, everything else cancels in that part of it, plus 2xy dy dx is equal to 0. Now, when you solve an equation, you want to isolate the variable of interest. In this case, the variable of interest, the variable, is dy dx. All right? So I want these two things to be isolated. I want this one and this one to be isolated, but I also need to consolidate them. Bottom line is the 2xy and the y squared have to go. All right, let's get that out of there. So I'm going to say x squared dy dx plus 2xy dy dx is equal to, if I get rid of these, I'm doing it through subtraction. So I'd subtract off a 2xy, subtract off a y squared. Then you look at the left-hand side, and you see, hopefully, there's a common dy dx to each term, as in a greatest common factor, the GCF approach. All right, so we can factor out, I mean, you can factor out more than just a dy dx, but since that's the thing that we're trying to isolate, it makes sense to just factor that out. So dy dx times x squared plus 2xy. Whenever you have multiple dy dx's, you're going to have to use this approach, the idea of consolidating and then factoring. But then to get dy dx alone, it's dy dx times this binomial. All right, so divide by that binomial. And you'll get dy dx is equal to negative 2xy minus y squared all over x squared plus 2xy. That's a fun one, obviously. Tomorrow I'll show you how to take the second derivative using implicit differentiation. And if I remember, I'll do it with this problem. That'll be the new part B. Find the second derivative. All right, so more on that later.